In the today's class, we are going to see about the methods of voltage control. So there are several methods of voltage control. In each method, the system voltage is changed according with the load to obtain the fairly constant voltage at the consumer end. The following methods of voltage control in the AC system are: so by using excitation control, by using tap changing transformers, by using the auto transformers, auto transformer tap changing settings, then boosted transformers, induction regulators, and by the synchronous condensers. So here, excitation control is one of the old method, mechanical control method. So nowadays, latestly, they are going for this tap changing transformers, on-load and off-load. Auto transformers also, it is not using. Booster transformers, sometimes they are using. Synchronous condenser, they are using at the generating stations, etc. So today we are going to see these things, how the voltage is being controlled. We are coming to the tap changing transformer. This is the offload tap changing transformer. So this is the primary winding. What is meant by a transformer? Transformer is a static device or a static equipment which changes the one form of the voltage to the another form of the voltage without changing the frequency. So frequency remains constant. Only the voltage we are stepping up or stepping down. In the generating station, what we are doing is we are just stepping up the voltage. And why? Because for it has to travel for very long distance. So after that, at the distribution end, at the substation, we are stepping down. We are stepping that down to 440 kilovolt to 220 kilovolt. Again 220 to 110 kilovolt. Again 110 kilovolt to 66 kilovolt. Then 66 to 33 kilovolt. And you can see some of the substation nearby your place. You will be finding most of the 33 bar 11 kilovolt substation. 33 bar 11 kilovolt substation. From that substation only, all our nearby pole mounted distribution transformers are connected. That is of 11 kV bar 415 voltage supply. From that substation only, all our distribution transformers, that is DT, is connected. So many distribution transformers, maybe of 10 to 20 DTs might be of connected, and 3 to 4 areas may be connected to that particular substation. Each area is connected via one feeder. And also sometimes your industry, if you are having if you are staying near to the industry, so that also they will have a separate feeder. So if they open that feeder, that particularly in that industry alone will be islanded. Like that also they may plan in the substation. And if you see this offload tap changing transformer, yeah, this is the primary winding, this is the secondary winding. In the secondary winding, you have some most of the tappings. So here, this is the arrangement where number of tappings have been provided on the secondary side. As the position of the tap is varied, the effective number of secondary turns also get varied, and hence the output voltage of the transformer can be changed. If this movable arm varies, the output also will be changed. When the movable arm makes contact with the stud 1, when the movable arm makes contact with the stud 1, the secondary voltage is minimum, and when this movable arm is connected to the stud 5, then it is maximum. So during the period of light load, the voltage across the primary is not much below the alternator voltage, and the movable arm is placed on the stud 1. When the load increases, the voltage across the primary drops, but the secondary voltage can be kept at the previous value by placing the movable arm to the highest stud. So depends on the voltage range, whichever the voltage range you want. You want less voltage range, then you have to connect this movable rod to this stud 1. If you want more voltage, you have to connect this movable arm to stud 5. So if you want medium, you have to connect 3 to 4, like that, whichever the voltage you want in the secondary side. But one of the major disadvantage in this soft load transformer is that while doing this operation, that is while changing this operation, what they will do is that the secondary side, the load will be disconnected for some seconds, for some 30 seconds or 60 seconds. This load will be disconnected. Then manually what they will do is they will change this movable arm. They will change this movable arm. Again, they will close this feeder. There will be a feeder here in the secondary side. So in secondary side, automatically they that feeder will be opened, and then they will move this this movable arm. So what is the main disadvantages in that? The load that here only we are connected, that is consumers, domestic consumers as well as industrial consumers are connected in this side. So we'll get some flip in the voltage for some seconds or some minutes. So some 30 seconds we'll get power off. Then they will manually they will move, and again they will open. Again they will close this feeder, so that we'll get the flip in the things. Like you will be watching the TV or cricket or something like that. Your favorite news or favorite programs will be going on. Suddenly there will be a power off. There will be a power off for sometimes some seconds, some 30 seconds. So then they will on that on the feeder. So this is the major disadvantages of using this off-load tap changing transformer. Coming to the on-load tap changing transformer. So this on-load, so this is the structure, like a primary side. In the secondary side, so in the supply system, tap changing as normally to be performed on the load, so that there is no interruption to the supply. So here in the on-load tap changing transformers, there is no interruption in the supply. The figure shows the diagrammatically type of on-load tap changing transformer. The secondary side consists of two equal parallel windings. It is divided like that. Two equal parallel windings which have similar tappings. From 1A, 2A, 3A, 4A, 5A, like that. Similarly, here also 1B, 2B, 3B, 4B, and 5B. And also here, two switches are there, A and B. Two switches are there. In normal working condition, the switch A and B and the tappings with the same number remains closed. In the normal condition, switch A and B remains closed, and the secondary winding carries one half of the total current. So secondary winding carries one half of the total current. So as by the figure, the secondary voltage will be maximum when switches A and B and 5A and 5B is closed. Same like what we have seen in off-load transformer. No, the same like similarly like when 5A and 5B and only switch A and B alone will be closed now, then the secondary side will be of maximum. Like voltage will be of maximum. However, the secondary voltage will be minimum when the switch A and B and 1A and 1B are closed. When this A and B is closed, again this 1A and 1B alone will be closed this time. So here the voltage will be very minimum, in the secondary side. Suppose that a transformer is working with the tapping position 4A and 4B. 4A and 4B. It is desirable to alter this position to 5A and 5B. For this purpose, one of the switch A and B, say for example, A is open. This takes secondary winding controlled by a switch A out of the circuit. Now the secondary winding controlled by switch B carries the total current, which is the twice its rated capacity. Suppose, say for example, this 4A and 4B is closed, A and B are closed. Suppose you want to change from 4A to 5A and 4B to 5B. So what you have to do is, you just open this one, say for example, open this one A alone, and you change the tappings to 4A to 5A, and here also 4B to 5B. So B is closed. So this alone, this side alone carries the twice the like a voltage. Okay, this winding carries the twice the total voltage. So this takes the Now the secondary voltage controlled by the switch B carries the total current. So here this secondary voltage alone carries the total current, which is twice its rated capacity. Then the tappings on the disconnected winding is changed to 5A and the switch A is closed. After this, switch B is open to disconnect this winding. After again switch B is open, again the same, switch A is closed. So again you have to change this to 4A to 5A, like that. After this, switch B is open to disconnect its winding. Tap position on the winding is changed to 5B, and then switch B is closed. In this way, tap position is being changed without interrupting the supply. So those who are connected, we are connected here, no secondary side. So we are not get any interruption. We are not got any interruption while we connected at this position. So next, during this switching, the impedance of the transformer is increased, and there will be the voltage surge. So ultimately, impedance of the transformer will be increased. There will be the sudden voltage surge. There are twice as many tappings at the voltage steps. Okay, this is the main disadvantages. Impedance will be increased, and there are twice as many tappings as the voltage steps. Next, coming to the auto transformer tap changing settings. So here in this figure, showing the auto transformer tap changing settings. Here, a mid-tapped auto transformer or reactor is used. So this is the mid-tapped. This is the auto transformer reactor. Auto transformer or reactor is used. One of the lines is connected to the mid tapping. See here, the secondary side is connected to the mid tappings of this auto transformer. One and say A of the transformer is connected to the series of the switch across the odd tappings. A of the switch is connected across the series of the odd tappings, and the another end B is connected to the switch across the even tappings. So another B is connected to this tappings. Okay, switch A is connected to this short circuiting switch, and the switch B is connected to this connected to the switches with the even tappings. So a short circuiting switch is connected across the auto transformer and remains in the closed position under normal operation. A short circuiting switch is connected across this auto transformers, and it is always closed in the normal operation. In the normal operation, no inductive voltage drop across the auto transformer. So in the normal operation, there is no inductive voltage across this auto transformer. it is clear that with the switch 5 is closed, minimum secondary turns are in the circuit, and hence the output voltage will be lowest. On the other hand, the output voltage will be maximum when switch 1 is closed. When switch 1 is closed, the output voltage, this is the secondary side, this is the primary side. Whereas in the previous figure, this is the primary, this is the secondary. But for clear understanding, so this side is shown as the secondary side, and this side is shown as the primary side. So while drawing, you should very, very careful about this primary and secondary side. So if you draw, if you write this as a primary side and this as a secondary side, the whole thing is wrong. Even though you written well, the whole thing is wrong. Only 0 marks will be awarded. So here, if switch 1 is closed, then maximum voltage is connected. If switch 5 is closed, then the minimum secondary turns is connected to the circuits. On the other hand, output voltage will be maximum when switch 1 is closed. Suppose now it is desired to alter the tapping points from position 5 to position 4 in order to raise the output voltage. For this purpose, short circuit switch is open, then switch 4 is closed, then switch 5 is open, and finally short circuiting switch is closed. In this way, tappings can be changed without interrupting the supply. Suppose you want to change from 5 to 4. So by that time, what we'll do is we'll just open this short circuiting switch, so that you can change. You can open this tap 5 and you can close this tap 4. Again, you have to close this short circuiting switch. Yes, understood, no? So again, you have to close this short circuiting switch. Yes. In this way, tapping can be changed without interrupting the supply. So interruption in the supply is not there in this secondary side. In the meanwhile, when the short circuiting switch is open, the load current flows to the one half of the reactor coil, so that there is the voltage drop across the reactor. When switch 4 is closed, the turns between the points 4 and 5 are connected to the whole reactor winding. A circulating current flows through this local circuit, but it is limited to a lower value due to the high reactance of the reactor. So next comes to the booster transformer. Booster transformer. So suppose if you are located in the very far place from the far away from your substation. Say your substation is at one end in the roadside. Say your house is being located in the somewhat 5 kilometers, 10 kilometers far away from your substation. In that scenario, say for example, you are the ultimately last. You are at the last end of that the poles, that particular that substation is being connected. You are that last end. In that scenario, you will be receiving the voltage. As I said, the voltage what you received is very, very low, like 150 voltage, 160 voltage, like that. Your ceiling fan may be running very, very slow. Like your refrigerators will take much of the time. Your refrigerators will give some sound. Sometimes your washing machine will not run. Only the sound will come. It will rotate, but the whole process will not be done. It will be taking if you just enter 30 minutes of time in your washing machine. Even if it takes 1 hour, also you're still that washing machine will be running, not doing the operation. Will be just rotating, but not doing the particular operation. Like that, many misbehave will happen. Your iron box will not heat it up. You have to wait. Still, you are waiting for 10 minutes or 15 minutes. Still, your iron box will not be getting heated up. Like that, your all the things might be misbehaving. Your mixes might be running very slowly. Okay, so if it is runs at 1500 RPM only, the whole thing will be grinded properly. Otherwise, that is also running slowly. Like that, many things is misbehaving. So due to the you're located in the farther away from the main transformer, that is distribution transformers where you're connected. So in that case, what you say, for example, you are making a complaint to the electricity board, like we are not receiving this much voltage, that is 230 voltage or minimum 180 or 190 voltage. So like you're raising the complaint. So by in that scenario, your electricity board will install a boosted transformer in near to your area. Yeah, say for example, in that particular area, some 30 connections are there, or 40 connections are there in the farther end. Some colony is there, some 30 to 40 connections are there. So in that 30 to 40 homes itself, we are not receiving that much voltage, and the voltage is what we are receiving is very, very less. So in that scenario, they will install a boosted transformer in that particular area. So boosted transformer is connected in the series with the line whose voltage will be controlled. Like if you're seeing in this diagram, no? Sometimes it is desired to control the voltage of the transmission line at the point far away from the main transformer. That is, say for example, this main transformer is nothing but your substation transformer or distribution transformer also. The secondary of the booster transformer is connected in series with the line whose voltage is controlled. The secondary of this booster transformer is connected in the series with the line whose voltage is to be controlled. The primary of the transformer is supplied from a regulating transformer fitted with on-load tap changing gear. The primary is connected to the regulating transformer fitted with the on-load tap changing gear. So this is the on-load tap changing gear. That is the primary is connected like this. Secondary is connected with in the series with the line. So those who voltages being connected. So this booster transformer is connected in such a way that secondary injects the voltage in the phase with the line voltage. So secondary injects the voltage in phase with the line voltage. So the voltage will be injected in the phase with the line voltage, so that your voltage range might be kept constant. Say for example, here the voltage at AA, this is the AA point AA, is maintained constant by tap changing gear in the main transformer. However, there may be considerable voltage drop between AA and BB, due to fairly long feeder and tap changing of the load. The voltage BB is controlled by use of regulating transformer. This is one of the regulating transformer and booster transformer. By changing the tappings on the regulating transformer, the magnitude of the voltage injected into the line can be varied. This permits to keep the voltage at BB to the desired value. So here, this is the figures. This is the figure of booster transformer. You will be finding this booster transformer either in the substation or sometimes in the farther places. If you go to deep villages, you will be finding this. Apart from the distribution transformer, you will be finding this kind of booster transformer also. But the main disadvantages of this booster transformer is it is very most expensive than the on-load transformer instead of on-load tap changing transformer. So secondly, this is less efficient owing to losses in the boost transformer. So losses will be heavy because it is connected in series. The losses will be heavy. And thirdly, more space is being required. So more space is being required. You have to install like a transformer yard. Okay. So you have to buy a land, of 10 feet to 10 feet, like land, and you have to install it at like a transformer yard. Then again you have to install a pole. Again you have to install a booster transformer. That is of most expensive. So this and all will get. So like previously like 15 years back, you will be finding the most of the booster transformers in many areas. And after 2010, 2012, the Ministry of Power, they decided to eradicate all this booster transformer by using the distribution transformer itself. So they plan to install more distribution transformers. So two or three streets once, they have to install a distribution transformer, so that your losses will be decreased, and also voltage level also will be maintained at the constant value. So they have replaced all this. But even though you'll be finding one or two places, you'll be finding this kind of booster transformers still in the operation. But after that, they reduced after 2012. They reduced installing many booster transformer to, and they changes that to this distribution transformers, pole mounted distribution transformers. Yeah, this is the figure of three phase transformer. Similarly, here it is, the booster transformer is connected like this. Three phase. This is the figure of three phase booster transformer. Next, coming to the, yeah. So next is synchronous condenser. I think this topic you have studied in your electrical machines. So when the synchronous generator is overexcited, in that scenario, it is acted as a synchronous condenser. Okay, so it will synchronous condenser. The voltage at the receiving end of the transmission line can be controlled by installing specially designed synchronous motors called synchronous condenser. So synchronous motor, when it is overexcited, it is acting as a synchronous condenser at the receiving end of the line. The synchronous condenser supplies wattless leading kVA to the line depends upon the excitation of the motor. The wattless leading kVA partly or fully cancels the wattless lagging kVA of the line, thus controlling the voltage drop in the line. In this way, the voltage at the receiving end of the transmission line can be kept constant as the load on the system changes. So this synchronous condenser is being installed at the receiving end of the line. That is, synchronous motor, when it is overexcited, it is acts like a synchronous condenser. In laboratory also, we can one time we can see when it is overexcited, it will be acting as a synchronous condenser. Yeah, so this is like same like synchronous motor only. Only thing is that it is overexcited. By in that time, it is acted as a synchronous condenser. Next is voltage control by using the shunt capacitors. Shunt capacitor banks are used to supply reactive power at both transmission and distribution levels along the lines or substation and loads. So if you visit a substation, there will be a separate capacitor, shunt capacitor bank room. One room will be there in the substation. I will show you a video if possible, meanwhile in the forthcoming class. So in that scenario, you will be finding one, particularly one room will be there. So in that room, like a serial, shunt capacitor banks are being connected. Okay, shunt capacitor banks are being connected. so that it will supply the reactive power. Sometimes if the power factor, you have to maintain the power factor constant. So like that, simply like that, if they just open this shunt capacitor banks, automatically your power factor also will be maintained. And also if you want to supply the reactive power at both in the distribution levels and as well as in the transmission lines, in the switching substation, as I said, 440 bar 220 kilovolt substation, like that, shunt capacitor banks is used. But that too, the ratings are of very high. But even though there will be shunt capacitor banks, so that might be used in the some emergency situations to supply the reactive power, because without the reactive power, the power flow will not be there. That we'll be seeing the next thing, that is the power factor thing. Then a capacitor are either directly connected to the bus bar or tertiary winding of the main transformer. They may be switched on and off depending on the changes in the loads, having a lagging power factor. If it is lagging power factor is there, simply they will switch on the series that is shunt capacitor bank, so that lagging power factor will be leading and it will be maintained constant. Shunt capacitors are extensively used in industrial and utility system at all voltage levels. By developing higher power density, low cost improved capacitor and an increase in energy density by the factor of 100% is possible. Then these present a constant impedance type of the load, and capacitive power output varies with the square of the voltage. That is kVAR V2 is equal to kVAR V1 V2 divided by V1 the whole square. So where kVAR V1 is the output at voltage V1, and kVAR V2 is the output at voltage V2. As the voltage reduces, so that the reactive power output when it is required the most. This is called destabilizing effect of power capacitors. Capacitors can be switched in certain discrete steps, and does not provide a stepless control, as the reactive power demand increases with the voltage falls. Where what is the main advantages is very less costly, then flexibilities of installation and operation, then power factor improvement will be there. Then efficiency of the transmission and distribution of power is high, so it will maintain the efficiency in the transmission and distribution side. Single or multiple banks in industrial distribution at low and medium voltage substation. So this shunt capacitor banks in industry is also very important. Without this, I think no industries is there. Even in our college also we'll be having this shunt capacitor banks, or sometimes they are utilizing to maintain the power factor constant. Almost if you find 99.9 industries, that is 100% industries having this shunt capacitor banks. Without this shunt capacitor banks, your power factor will be not maintained constant. By the time, what they will do is for industries, they will come for the frequent checks from the electricity board, distribution corporation sectors. Assistant engineers or executive engineers will go for a frequent rates. It will be called rates or frequent checks like that. So by in that trade, if they are not maintaining the power factor constant, or if they are not maintaining the reactive power, they will be fined with the power factor tariff. Power factor tariff that might be of one by half of your electricity bill. Say a company is paying electricity bill of 2 lakhs per month, means they have to pay around 75,000 to 1,75,000. They will be severely charged. So 75,000, the sense almost 40% to 50% they are paying. So 40%, 50% paying means then automatically your profit of that particular company will goes down. Then definitely five people will lost their job. Five people will lost their job. So in industrial sector, this maintaining the power factor is very, very important. Otherwise, that electrical in charge will be losing their job, or the company will be given with a penalty tariff. Severely, they will give the penalty tariff. That also that. So the maintaining the shunt capacitor banks, whenever the power factor is leading, whenever the power factor is lagging, they will simply on this shunt capacitor banks for some time, so that it will comes to the constant thing. And it may depends. Nowadays, due to the modern technology, the feedback also given automatically. It is being on. Automatically, it is being switched on. How much banks, how much capacitors if they want to on like that, automatically is switch it on, switch it off like that. Also, it is happen. And what is the main disadvantages? It cannot be overloaded, and reactive power supplied by the static capacitors tend to decrease in the case of the voltage dip on the bus, because kVAR is directly proportional to voltage square. Then what are the problems associated with this shunt capacitor? Switching inrush current at higher frequencies and switching over voltage. Harmonic resonance problem will be there. Next, limited over voltage withstands capacity. Limited of harmonic current loadings. Possibilities of self-excitation of motors when improperly applied as a power factor. Improperly power factor improvement capacitor switched with the motor. Main applications is improves the power factor, improves the feeder voltage control. So even though some limitations are there, even though this shunt capacitor banks is being used in the many of the industries, and as well as for substation, and as well as in between the transmission line, that is switching substation. Next, coming to the series capacitors. Series capacitors is connected in the series to compensate the inductive reactance of the line, that is XL, inductive reactance of the line. This reduces the transfer reactance between the fuses to which the line is being connected. It increases the maximum power that can be transmitted and reduce the reactive power loss. So this is being connected in the series to the line, which compensate the inductive reactance, and as well as is reduce the transfer reactance between the fuses to which the line is connected. So it increases the maximum power. So maximum power is being increased in the that can be transmitted and reduce the reactive power losses. Reactive power losses is being reduced. The reactive power produced by the series capacitor increase with the increase in the power transfer. A series capacitor is a self-regulating in this regard. Under the fault conditions, the voltage across the capacitor rises. Voltage across the capacitor rises, and unlike the shunt capacitor, the series capacitor experience many times its rated voltage due to the fault currents. So under some fault conditions, the voltage across the capacitor, this capacitor, series capacitor, will be rises, and unlike a shunt capacitor, the series capacitor experience many times its rated voltage. So this will increase many times its rated voltage. So if you say like this is the sending end voltage, this is the receiving end voltage. So sending end, sending end, you are sending 11 kilovolt. In the receiving end, you will be getting more than the sending end, that is 15 kilovolt or 13 kilovolt, like. So more than the sending end, receiving end will receive. So in that scenario, what they will do is they will install a zinc oxide variester is connected in parallel with a capacitor, may be adequate to limit the voltage. So here zinc oxide variester is being connected with the parallel to the capacitor so that it limits the voltage. For the locations with the high fault currents, for the location with the high fault current, a parallel fast acting triggered gap is introduced. So in the high fault currents in that particular location, this fast acting triggered gaps is being introduced, which operates more severe faults. When the spark gap triggers, it is followed by the closure by the bypass breaker. So any major fault is being happened in this particular line, automatically this gap is being fire. Some fire will be triggered. Okay, so due to the high fault currents, a parallel fast acting triggered gap is introduced, which operates for more severe faults. When a spark gap triggers, it is followed by the bypass breaker. So here, so fast spark will get triggers. So automatically this will be compensated. Due to the high fault currents will be compensated by using this spark gaps. The drainage reactor limits the frequency and the magnitude of the current to the capacitor when the when the gap sparks. In this gap spark, this reactor also limits the frequency and magnitude of the current to the capacitor. To the capacitor, this also will be safeguarded this capacitor. So this schematic is being shown here. So coming to the phasor diagram, this is the single line diagram where this reactor is there, X is there, reactance is there, then capacitor is there. This is the sending end voltage, this is the receiving end voltage. Sending end voltage E, receiving end is VR. Okay, so here if you see the phasor diagram of the series capacitor, the current is okay. The current and voltage will be will be separated by this angle phi 1. But usually this voltage and current, if it will be in the same axis, then the same axis. This is correct. That is there is no phase difference. So by using the series capacitor, this is being this inductive, that is XL, this is being reduced. IXL is being reduced in the line. So this is the I into XC. But this lagging current will be always there due to the load is being connected. But in the ideal case, like normal case, this voltage and current will be in the same axis. Like I'll be explaining you clearly in the power factor explanation. So this is what are the drawbacks of the series capacitor? High over voltage is produced across the capacitor terminals under the short circuit condition. So sometimes any short circuit conditions is being happening due to the fault. In that time, high voltage is produced across the capacitor terminals. Therefore, very high protective equipment is used. That is spark gaps. Spark gap is being used here. Yeah, this is the spark gaps is being used here. Next, therefore, very the drop across the capacitor is if it is XC, where if the fault current of the order of 20 times the full load current under the certain circuit condition, like 20 times the full load current is being increased, if the fault current happening. The reactive power supplies capacitor. Reactive power supplies the capacitor is proportional to the square of the line and the current, which is independent of the line voltage. That is, so you know, like V is equal to IR. So here it is XC, that is inductive reactance. When this VAR, this VAR is being increased, defaultly the current is being squared. So 2 times, that is reactive power supplied by the capacitor is proportional to the square of the current and independent of the line voltage. So what are the locations? It is located at the midpoint of the line, or 1/3 or 1/4 of the point of the line. This is the location, so that you can locate the series capacitor. Next, coming to the problems associated with this series capacitor. Locking of synchronous motor during starting, then hunting of synchronous motor at a high load due to R/X ratio will be there. Ferro resonance also will be occurs between the transformer and series capacitor, which produce harmonic over voltages. That is 2 times, whatever the voltage is being sent in the sending end voltage, the receiving end, it receives 2 times than the sending end voltage. So that is called the ferro resonance effect. So what are the advantages? Series the main advantages are to improve the voltage regulation of the distribution and industrial feeders will be there, to reduce light flicker problems. This series capacitor is being used. Next, to improve system stability is there. To improve the system stability, this series capacitor is being used. Main applications, the voltage rise due to the reactive current by the bypassing the capacitor during the fault, after reinsertion, after the fault clearing. So during the fault, simply like that you can bypass, so that if you didn't bypass means this capacitor will increase the that fault current to double the times, so that the current will be increasing like anything. Then the size of the equipment in the substation will be, you have to increase the size of the equipment. How to increase the size of the equipment? You have to increase some other, you have to on some other transformers. Then the size of the conductor also might be increasing. So many corona effect also will be coming, humming noise will be there. Then losses might be of anything. Then heat loss might be there. So there are many disadvantages. So by that, whenever the fault current is happening, automatically some circuit breaker has to disconnect that particular capacitor, that is series capacitor, so that it will not affect that much. If you connected wire during the fault, then it is very difficult. That is 2 times the current is being increased. So the entire system will get collapsed. Next. Yeah, these are the things for the voltage improvement. That is, first thing we have seen the off-load tap changing transformer, on-load tap changing transformer, then booster transformer, then synchronous condenser, then shunt capacitors, and as well as series capacitors for this voltage improvement.